Hello Ostrava. The music you're about to hear is made of the waveforms you're about to see, played back on an oscilloscope. One of these
Dobrý den. There's only 3 words of Czech, I'm afraid I will say today, and you've just had 2 of them. So yeah, I would like to tell you a little bit about antimatter. It's very commonly talked about in popular culture. I'd like to try and separate the science bit from the science fiction. So most people encounter antimatter in science fiction. I think the most obvious place where it occurs is in Star Trek. The Starship Enterprise, however many is it now, 8 of them, are all powered, apparently, by antimatter. They have these magic dilithium crystals. We don't know what a dilithium crystal is, they made it up, which somehow contains antimatter, and they use the power of that antimatter to drive themselves faster than light through the universe. Other science fiction does this. This probably doesn't play well in a Czech audience. I'm a big fan of Doctor Who. I'm glad some people know it. Good. I've been a fan all my life, so all the old stuff as well as the new stuff, and it appears all the way through Doctor Who's history. So, you know, that's partly what got me into science, actually. Okay. It also appears in really bad science fiction. Am I allowed to say this? It appears a lot in the film Angels and Demons, where a wicked pope steals antimatter from CERN and gets enough of it to build a bomb that's going to destroy the Vatican. I've never worked out why, and I've read the book and I've seen the film, and that's 3 hours of my life I will never get back. But anyway, that was actually partly filmed at CERN. I'm afraid Chris left this morning, but Chris Thomas, who was working with us the last couple of days, his head appears in that film as they zoom down towards the experiments. Okay, but antimatter is real. Antimatter is stuff of the real universe, and in a sense, the stuff of everyday life, but we don't encounter it very often, and that's the mystery that I want to talk about. It's actually even practically useful. I hope nobody in the audience has had the first example I'll come to of where it's being used. That's a thing called a PET scanner in hospitals. But it is there, and it's practically useful. And it was first proposed by, I'm normally talking to a British audience, so I call him a British physicist, Paul Dirac. He was actually born in Britain, but if I was in Switzerland, I would call him a Swiss physicist because his parents were Swiss. Okay, we steal everything. And he was working on a really important question in 20th century physics. There were 2 very big ideas that appeared in the 20th century in physics. I'll tell you a little bit in one slide about each of them. One of them was relativity, and the other thing was quantum mechanics. And he was trying to write down an equation that described how matter behaved that was both quantum mechanical and relativistic. And that was a difficult problem that had some surprising results. So I'll tell you a little bit about relativity. So in the end of the 19th century, something rather surprising was observed. That was that if you measured the speed of light, it didn't matter how fast you were traveling or the source of light was traveling, you always measured the same speed. Now that may not seem profound, but actually that's very disturbing for a physicist. I'm going to ask somebody with a little bit of space to move. There's too crowded here. Just to illustrate it, if this is science, it's a beach ball, it must be real science. Okay, that lady there, perhaps, I think you just have enough room to move. Would you mind first catching this ball? I throw this ball at you. Oops. Actually, I hit the gentleman there. Can you throw it back? Okay. That traveled a certain speed. I'm now going to, sorry, I have to do it this way round because I'm the only one with space to move. I'm now going to run at you and throw the ball at you at the same speed, with the same force. Now, from all the stuff you learned at school, you would expect that the ball was traveling faster the second time because it had the speed I'd thrown it plus the speed I was running. Yeah? If you think about when you're coming towards a car, you see that car coming towards you with your speed plus its speed. That doesn't work with light. As you're driving towards the light, it always comes towards you at the same speed, even if it's traveling, being emitted by something coming towards you at almost the speed of light. You still measure the speed of light. That is profoundly disturbing. That led Einstein and others, but mainly Einstein, to construct a whole new form of physics because the laws of Galileo and Newton do not describe a behavior like that. So Einstein and Lorentz and others set up some rules which tried to describe a system which would explain this. That we call relativity, and it has many surprising results. We found that the rate at which time passes depends on the relative speed of you and the thing that you're observing. You find that in general relativity, an extension of the theory, light can be bent by gravity. And that was confirmed not long ago. It was in 1919. It's 100 years ago. That observation was confirmed, that the positions of stars close to the sun when there was an eclipse apparently were moved by the mass of the sun, bending the light around the sun. And then the most famous thing that you've probably heard of relativity is that energy and matter can be converted into each other, and the equation that tells you how much energy converts into how much matter, mass, is E equals mc squared, where c is the speed of light. So you multiply the mass by the speed of light, and then you multiply it by the speed of light again, and you get the amount of energy that's equivalent to that mass. We'll use that equation a little bit, we won't do sums, we'll talk about it a little bit later. The thing is that relativity tends to be important at high speeds and at large scales, so the scale of stars and planets and galaxies, and at very high velocities. Another revolution that happened in the early 20th century was something called quantum mechanics. That came out of another apparently trivial effect. They were looking at the behavior of metals when light shines on it, and you see that sometimes electrons, little particles, are ejected. And that told them something profound, because up until that point, they had assumed that a system can take on any value for its energy. You just put in a little bit more, it goes up in energy, and it can take any value. What this effect showed you was that this photoelectric effect, the electrons could only take certain values of energy. You could only put in certain amounts of energy to make them jump between those different values of energy. And then that behavior was observed in many other things. It explained why atoms are stable, for instance. And so that quantization, that's what the quantum in quantum mechanics comes from. It's the fact that these things can only take discrete values, not a continuous set of values, showed you many, many strange things. It showed you that, for instance, the particles are behaving sometimes like waves, and that waves are behaving sometimes like particles. We call that wave-particle duality. And in a sense, a consequence of that is that there are various relationships which we call uncertainty relationships, the uncertainty principle. So, for instance, if you know the precise position of a particle, you have essentially no understanding of how fast it's going, what its speed is, what its momentum is. And the more that you know its momentum, the less you know its position. That's a consequence of the fact that the particle is really something between a particle and a wave. There's another relationship which is also relevant to later in the talk, which is similar, and that's if you know the time at which an event occurred, you have less and less knowledge. The more precisely you know that, you have less and less knowledge of the associated energy of that event. That's another uncertainty relationship. These strange quantum effects are usually low scale. Back in my lab, we do a lot of ultra-low temperature physics, and actually we can show you quantum mechanical systems in a bucket. But it tends to be at very small scales, but it is usually as well seen at very low temperatures. Okay, those are two very strange and different theories. The problem is, how do you put them together? Now, Dirac was not the first person to try and marry those two theories into one, but when people had tried that, they had found very strange results. They found whatever they did, they get solutions for the particles that say that these particles would have negative energies. And that makes no sense to a classical physicist. What is a negative energy? It seems like a mistake. Dirac's genius was not to get rid of the negative energies. What he realized was it was telling you something about the way the universe works. He was actually realizing that this was pointing you towards the fact that there is not just ordinary matter, there is antimatter. Actually, at the same time, for those of you who've done high school physics or chemistry, you probably remember that particles have an intrinsic spin property. It also shows where that spin property comes from in the same piece of work. It was a very impressive piece of work. What was the idea? Well, the idea was that actually the negative energy states are real and they're with us all the time. But he assumed that all of those negative energy states, which are at different discrete values, remember this is quantum mechanics, so that they can't be any value, they're at discrete steps up this ladder of energies, they're all full, normally. But what he realized was, if you send in some energy, usually a particle of light, in principle you could take a particle from that sea, he called it, of negative energy states, and you can push it up in energy so it has a positive energy state, so it can appear up there. And then he said, well, what would that look like? Well, he said, well, you'd see a particle appearing, an electron, say. But what would be left? What would be left in the sea is the absence of an electron, which would have the opposite properties. It would have the opposite charge. It would have the opposite magnetic properties. Let me give you a little example of this. Sorry, to make this work, I have to jump back a slide and then jump forward. Look at the image in the we have here. This is a relief. It's of Einstein's face. But when you look at it, it's an optical illusion. But first of all, try to work out, are you looking at a depression into something in the shape of Einstein's face, or are you looking at something which comes out of the surface like Einstein's face? So I'll go back and come forward. Oh, here we go. So you see it turning. Is that the whole, or is that the positive? Can you tell? And now we get the positive. Yeah. But the point is that they look very similar. And this is just an analogy, but to try and explain this idea that by removing something from this sea that we didn't know about before of negative energy states, the whole looks very like the thing you've taken out of it. It looks like the electron, but actually it's got all the opposite sense. It's the depression values, not the sticking out values. Yeah? Okay. Now, some people thought that was crazy. Bohr was one of the great physicists of the 20th century. No one should argue with that. But he dismissed this idea as madness. Unfortunately, this prediction was made in 1931. People went back and looked at cosmic ray data, and I hope you take the opportunity to join some of our cloud chamber workshops where you can build a cosmic ray detector with us. What he'd seen was an event like this. You may see something happening here, and then a gap, and then two particles curving in the opposite direction. There's a magnetic field. One of them is an electron appearing, and it curves one way because of its charge in the magnetic field. But you see something curving in the opposite sense in the magnetic field. And it has the same mass. You can measure it and work out the same mass. That was an electron, and then something that looks like an electron with all the opposite electrical properties. That's an anti-electron, a positron. That had already been observed in 1930 by a guy called Carl Anderson, but nobody had realized what it was until Dirac came along with the theory. I'm not going to be corrected on this, I hope. Okay, so what about the reverse process? You can take some matter and you can take some antimatter. What happens if you put it together? Well, that's where we come back to E equals mc squared. Because you're dropping your particle back to fill a hole. What happens, remember we put energy in, creating a hole in a particle. You drop the particle into the hole. What comes out is energy. And the amount of energy is governed by E equals mc squared. So the mass of the two particles turns itself into energy. And actually, you see photons coming out. Okay, that's where the idea of the bomb in Angels and Demons come from, because you can put the antimatter, it will collide with matter, and it will generate energy. Does that make sense for a bomb? Not really. We'll talk about that. But before I get there, I don't like telling people things which are not the current way we think about things. Since the 1950s, another great theorist, Richard Feynman, working with another physicist, Stockelman, also a great physicist. We're all great physicists, by the way. They had a new interpretation, which is actually closer to the way that particle physics thinks about antiparticles nowadays. What they realized is the antiparticle actually looks like the particle, but traveling backwards in time. So this is what's called a Feynman diagram. It shows an electron annihilating with a positron. That's the process that we would have had on the previous slide, turning into light, and then it can turn into another matter and antimatter particles. That's a quark and an antiquark, whatever. But you'll notice the arrow for the anti-electron, the one with the plus, not the minus, that's going backwards. That's viewed as a particle going backwards in time. So maybe when Star Trek uses the dilithium crystals to power itself through the universe, and occasionally you may remember they find themselves going backwards in time as a consequence, maybe they actually had a point. Okay, now, where do you see antimatter? Well, antimatter is being made all the time in particle physics experiments like the one that many of us in the team here work on, the ATLAS experiment at the Large Hadron Collider. In fact, in the collisions there, by the way, this is a picture of where the accelerator is. It's not really on the surface. That would be bad for the environment. It's actually a long way underground, and my studio flat is just down here, so if you're ever passing by, I'm happy to make you a cup of tea. So yes, you see the experiments are actually deep underground. It's located in the Geneva Basin near to the lake, and it goes under the Jura Mountains. It's between 50 and 150 meters underground. That's not because we're very clumsy when we make our accelerators. It's because the ground is rising. It is actually on a slight tilt, but we haven't got time to go into that. Okay, so it's about 100 meters underground on average. It's 27 kilometers in circumference, which is big. And we actually have protons accelerate particles which are in the nucleus. The simplest atom is the hydrogen atom. It's basically the nucleus of a hydrogen atom, huge swarms of them in bunches, and we circulate them in opposite directions, and we collide them. We use the energy of those collisions when we collide them together to produce new particles. We're using E equals mc squared again. Okay, this is where the ATLAS experiment will look like underground. The point is the accelerator is actually working at temperatures which are actually colder than free space. It's only just above absolute zero. So I tell my astronomy friends that particle physics is obviously cooler than astronomy. And each eighth of the accelerator is the largest superconducting system in the world. There was a little demonstration of superconductivity earlier this morning in the workshop with Badminton School. I think they're doing that again tomorrow if you want to see some of the effects of superconductivity. This is a cutaway view of the Atlas experiment. You may see, this pointer won't show up, tiny little figures. So it's really big. It's about 5 stories high, the Atlas experiment, but not that dense. It weighs a lot, 7,000 tons, but it's actually less dense than water. So in principle, we could make it float. But I don't think we're ever going to try it. You may also notice some other figures up here who are definitely breaching health and safety regulations. Okay. So when we do our collisions, almost, there's 2 matter particles going in, so it's not quite true, but almost half of what we produce is antimatter. In fact, almost any physics process we know produces essentially equal amounts of matter and antimatter. But in the Atlas case, the antimatter decays away, interacts very quickly. But this poses a deep problem for explaining how you and I are here today. So, would it be possible to make that bomb? Well, in the book, they had 0.5 gram of antimatter to try and blow up the Vatican. Well, if we could get that, and if we could put it in a good enough container, and if we could then transport it without it destroying itself, then in principle, we could make that bomb. For comparison, 1 gram of antimatter annihilating would release the equivalent of about 3 times the energy that was in the bomb at Hiroshima. It's about 40 kilotons of TNT. I might actually have tea. Okay. Thank you. I may have tea. I'm English. I've got to have tea. I actually live quite close to a nuclear power station in Lancaster. We have beautiful scenery and we have a nuclear power station. It's about 50 hours worth of the output of that nuclear power station will be liberated in 1 instant if you annihilated 1 gram of antimatter. So, all of the antimatter we produce in the experiments, though, is gone within a tiny fraction of a second. Now, the amount that we're producing, how would that translate into warming things up? So if we took all of the antimatter produced in our experiment and channeled it somehow to try and keep my cup of tea warm, it would raise the temperature of my tea by 1 degree Celsius per hour, which may sound impressive. It doesn't sound impressive to me. In fact, it's really not impressive because this tea is going cold. It goes cold by about 10 degrees Celsius an hour, according to Newton's law of cooling, so it wouldn't even keep my tea warm. Not a very efficient way of making a bomb. Now, how long would it take us to get that amount of antimatter? Well, we worked it out. It would take about 10 million years, which I don't think is a very practical way of doing your fiendish plot to change the Vatican structure. We actually have a facility at CERN that does try to capture antimatter. We're not doing it to make bombs. It does a much slower accumulation. That would take about 500 million years to get our gram of antimatter. There's an experiment called Athena. It stores at most about 1 million antiprotons in a magnetic bottle. You've got to keep the antimatter away from ordinary matter, so the only way you can store it is with magnetic fields. And that is 100 billionth of a gram. It's the most that we could actually store. The reason we've done it is to try and make anti-atoms and anti-molecules just to see if they behave the same way as ordinary matter, atoms, and molecules. And as far as we can see so far, they do. But there are practical applications to real antimatter. I mentioned earlier PET scanners. PET stands for positron, that's an anti-electron, emission tomography. Tomography is a way in which you can do imaging. And this is used in hospitals. It was developed at CERN, and you inject certain radiochemicals. We found actually there are some nuclei that you can make which will decay and emit an antiparticle. They will emit a positron. You can tag that, get it to go to a certain site in your body, usually where there is a tumor developing for cancer, and you can very precisely work out the structure and detail of that site, because the two photons that are produced when the positron is emitted, it immediately annihilates, and you can see, by looking back at the angle of these two characteristic photons, you can see precisely where they came from, and you can image what's going on inside the body. It's a tiny amount of energy release. It's much more beneficial to the patient than any risks associated with it. And this has helped many, many people around the world. There is actually even antimatter in the room today. This is something that sometimes my particle physics friends go, what's he talking about? But because of the uncertainty principles that I mentioned earlier on, there are always, even in empty space, particle-antiparticle pairs being produced for a tiny short period of time, because you can kind of break the law of conservation of energy in the universe for a tiny short period of time, so long as you give that energy back. So particle-antiparticle pairs appear and then recombine in tiny fractions of a second. That might sound like science fiction, but actually there are many effects where you can observe it. The most famous one is called the Casimir effect. Here, if you take two plates of metal in a vacuum, you find that there is a finite force between them, which is caused by the particle-antiparticle pairs being produced in the space in between them. They are polarized, it's like a little capacitor, and that actually has the plates having a force that pulls them together. I don't think anybody's ever worked out a practical application for this. Richard Feynman spent a long time trying to do that, but it's a real measurable effect. Okay, now to the fundamental question. The title of the talk is, what's the matter with antimatter? Well, all of the physics processes, apart from one or two, where there's a tiny difference, produce equal amounts of matter and antimatter, just like in our experiment. Now, are we lucky to be here? This chap has had an accident with his vehicle. He's come off the road, and he's just avoided falling off this cliff. He's lucky. Actually, he's immensely lucky. That's the drop. He's not half as lucky as he thinks. For us to be here, you might argue we're even luckier, because all of the matter and the antimatter in the universe from the Big Bang should have annihilated a long time ago. And if they're produced in equal amounts, there should be essentially nothing left to make us. Put it this way, what actually happened, there were 10 billion and 1 particles of matter produced to every 10 billion particles of antimatter. They annihilated, we call that the Great Annihilation, and what was left is the one part, and that's us. What is the physics behind that? No, actually, I want you to tell me what is the physics, because we don't know. We know a little bit about things that distinguish between matter and antimatter. There is one of the 4 fundamental forces, the weak interaction, we know will actually distinguish between matter and antimatter. You have to have certain symmetries broken to be able to have one decay away faster or be produced more than the other. But it isn't enough. So one of the things we're doing at the Large Hadron Collider is looking for processes that distinguish between matter and antimatter. In the introduction, you heard mention of beauty particles. These are particles that contain the second heaviest quark, the beauty quark. You don't have to understand this diagram properly, but there's a particle, for instance, called the B sub s. It's made of a strange quark and an anti-beauty quark. and that decays to two other particles called a J psi and a phi. We can look at that system and we can see you have the same decay if you had an anti-B sub s particle made of a beauty quark and an S anti-quark. But they don't quite decay the same way. They both decay to the same final particles, but they do it at slightly different rates, and we can measure those effects. That's one of the things that I'm very much involved in measuring. But it's not enough. It's about 1/10,000,000th of the amount of difference that we need to explain a universe that allows you and me to be here. There are other places where this sort of difference is visible. LHCb, another experiment at the Large Hadron Collider, has actually recently shown that there are similar effects distinguishing between matter and antimatter in what are called charm particles, where it's, instead of having a beauty quark, you have a charm quark. But it's still not enough. So somewhere we have to find more of this difference between matter and antimatter. Now, another place that people can look is not looking at particles made up of quarks, but they can look at a different class of particles, which the electron belongs to, and also the neutrinos belong to. They're called leptons. So, for instance, in my department, I have a group that's working on an experiment called T2K. That means from Tokai to Kamioka. So these are on opposite sides of the main island in Japan. And they are firing a beam of neutrinos across the island. The Japanese don't mind. Neutrinos interact so infrequently, nobody even notices that they're there. The point is that you can see one sort of neutrino turning into another sort of neutrino in a process rather like some of the processes we see in beauty quarks, in beauty hadrons, and they see evidence for small differences that allow a thing called CP violation. Again, that was mentioned in the introduction. There are small CP violating contributions which can come from the leptons. So that's another little contribution. It's another little contribution. It's again leaving us about with 1/10,000,000th of the amount of difference that we need to explain where we are. So it's a deep mystery. There is something the matter with antimatter, and we are trying to find out what it is. So, there are other mysteries, which I will say briefly. How long have I got?
About 5 minutes.
5 minutes, okay, that's fine. I just like to tell you, I wouldn't like you to think that what we do at the LHC is all about antimatter, so I'll just very briefly say a few other things. There's another very big question that we're trying to address in experiments like Atlas, and that's a different sort of matter. You may have heard of dark matter. There is, if you look at the astronomical evidence, then the universe seems to be made up more of a type of matter that we don't understand, and we don't know what it is, than the stuff that we do understand, that makes up you and me and planets and dust and stars. You can do it by looking at how galaxies rotate, and for them to rotate in a certain way, you know how much matter there has to be within the orbit of the particle that's going around the galactic center. And if you do the maths, a thing called a viral theorem, it will tell you that there is more material inside that orbit than we can account for by the dust, by the stars, by the planets, by you and me. And in fact, that's not just on the scale of galaxies. We can look at the behavior of collisions between clusters of galaxies, and we see the same effect there. There is something else there. It turns out that roughly 0.4% of the gravitating effects in the universe come from stars and things like that, stars and planets. About 3.6% of what's in the universe that's gravitating is intergalactic gas, and then about 23% of it is something we call dark matter. And while we have lots of theories, frankly, we can't tell you what the dark matter actually is, which is quite disturbing. It potentially means that there's more stuff we don't understand in this room than there is stuff we do understand in this room. What's even more disturbing is if you look beyond matter, the remaining 73% of what's causing gravitational effects is something called dark energy, which we've known about since the late 1990s, and frankly, even Atlas is unlikely to be able to tell you what dark energy is. There are lots of big mysteries going on. But we are trying to look for that dark matter. It fills space, but we barely interact with it. Atlas, we are trying to make dark matter particles directly. So there are theories like supersymmetry that say that there should be other sorts of particles, and they would have been made in great amounts in the early universe, in the Big Bang. But they decay away, and certainly in most of the supersymmetry theories, they decay away into the lightest supersymmetric particle, and then they're just left. They become what's called a relic. They're just lying around. If that's true, that would account for the dark matter. But if it's true, we should also be able to make those particles in our collisions if we have enough energy in the collision. And then there are other theories we look at. You may have heard that particle physicists and theorists are looking for other dimensions. This doesn't mean we're trying to get out of this universe, though when I look at the political situation in my own country, and to be honest, most other countries, I wish I could. But this is actually to do with theories that would try and tell us how to relate the different forces we know about, like gravity, like electromagnetism, like the weak interaction that I mentioned before, and another force called the strong interaction. And these extra dimensions are things that we can't ordinarily see, or if we do, we see it because of the way the forces behave. These extra dimensions express themselves in the way that, if they exist, in the way that forces behave. And these could explain why gravity, which you may think is a very strong force, but actually it's vastly weaker than the other forces, especially electromagnetism. It's much, much weaker. This could explain it with a single theory that says these two things are related, but because of the way these extra dimensions work, gravity would be very weak and electromagnetism would be very strong. So we're looking for evidence of these extra dimensions, if we can, in our data. And then the other thing we're looking for is the unknown. So when we go to high energies and to very large data sets, we can probe and look for new effects that have not been seen before. And we hope that takes us into new territory. The most exciting thing in science is not confirming things that people had predicted. Like, boring things like discovering the Higgs boson, which only gets Nobel Prizes. But actually things which people hadn't predicted, because it's those genuinely new things that take you into new territory and bring on the new ideas. So, I think that might even change our understanding of the nature not only of how particles work, but of space and time itself. So, the future. What's the matter with antimatter? Well, frankly, I know what the problem is, but I don't know what the solution is, but we're looking for it. The discovery of the Higgs boson, which I just dismissed, was actually a great milestone in the story of physics, but I haven't even had time to discuss that in this talk. But there's a lot going on in the subject. Many questions remain for us to answer, and I think if you just think about the questions I present to you, they're quite profound. We're asking, how is it we are able to be here? And if you're young and you're interested, or even if you're old and interested and prepared to study, why not come and join us? It's actually quite a good life. Doesn't pay well, but it's a good life. And you meet lots of nice people around the world. I think that's it for now. I promised you another word in Czech, děkuji. I have. Potentially, I will answer questions if people want to. I don't know if we have time during the session, but I will answer questions.
We have some time, few minutes for questions, so please ask questions.
And then I will ask too, because we have two giveaway prizes.
So please, questions.
Well, I'm glad it was so complete.
So somebody? Oh. Please try to ask the question very loudly.
Why has the matter mass?
Sorry?
Why has the matter mass?
That is a very good question, and that gives me a whole other talk. How long have you got? So, one of the fundamental problems we had in our theories of particle physics was that we had a beautiful theory, we call it the Standard Model, that was describing almost all the behaviors that we observe. We know there are missing bits, like the matter-antimatter question, but it was a beautiful theory. Very predictive, one of the most accurate theories ever contrived. The only problem is it doesn't have matter in it. It didn't have mass in it. How do the particles get mass? Well, you might think, all right, just give them a mass. But if you just give them a mass, it completely breaks the theory. It doesn't just say there's something missing, it actually breaks the theory. And that was a problem that was addressed in the early 1960s by Baruch, Englert, and Peter Higgs. And they came up with a theory which they could add to the standard model, which said that that they could account for the particles gaining their basic mass in a way that didn't break the rest of the theory. They said there must be a field all the way through the universe, a thing that we can interact with, a little bit like an electromagnetic field, but actually very different with what's called a scalar field. What does that mean? Well, it's basically reflecting the fact that if this thing is your interaction of your particle with that field is going to generate mass, it must generate the same mass, whether it's going that way, or that way, or that way, or that way, or that way. So it's the same in all directions. That's true only of something that is called a scalar field, which we don't often see. Temperature, for instance, is a scalar field. But it's the same in all directions. Electromagnetism isn't like that. The contribution that Peter Higgs particularly made to this, though, is he said, if that field exists, there should be a quantum of that field, a particle that you can make, which is made out of that field. Essentially, the field interacts with itself and produces a particle. And we said, great, well, let's go and look for it. Tell us, how does it behave? And they could tell us all of the different ways in which it would interact. And in principle, they could tell us how it would decay into different sorts of particles. The only problem was, we said, and how much does it weigh? Because when you want to make these particles, you need to build a collider that produces collisions of the right energy, that with E equals mc squared, you can make these Higgs particles. And they said, we don't know. The theory doesn't tell you the mass of this particle. So we started looking. People started looking in about 1965, and we found it in 2012. Sometimes you have to have patience.
Okay, thank you.
By the way, I should also say that most of your mass, even so, you need to have that for this to work, but most of your mass then doesn't belong to the Higgs field. It belongs to something called a strong interaction, which is the thing that's binding the nucleus together in the atoms and so on. So actually, most of the mass comes from the strong interaction. But you have to have the Higgs field there to give the original particles mass for that to work.
Thank you very much. And this was a very important question, but I'm very sorry because we don't have time enough.
Am I allowed two
questions? Some
questions? I have two questions. We have some giveaways. Strangely, I did a giveaway yesterday and we were giving away Atlas experiment things. This time I think we're giving away, one is Atlas and one is NASA. So, one question you can get from my talk. What is the mass, the weight of the Atlas experiment? First person to answer. Oh! Who was first? Lady here. Okay, that's one prize. And how long would it take Atlas to make 1 gram of antimatter? That was the Athena. Somebody else?
10 million years.
Yeah, that'll do. Okay, he gets it then. Oh, come on. Don't fight me.